4.2 light-years away, a planet slightly larger than Earth circles a red dwarf star, and scientists believe liquid water might flow across its surface right now. We call this world Proxima Centauri b, and it represents just the beginning of humanity's greatest discovery: planets beyond our solar system, where life could actually exist. Tonight, we journey to worlds where underground oceans hide beneath ice sheets, where one side burns in eternal daylight, while the other freezes in permanent darkness, and where the very air might shimmer with the chemistry of life itself. From planets with diamond rain to worlds where a single day lasts longer than our entire year, each destination brings us closer to answering the ultimate question. Before we launch into the cosmic unknown, hit that like button and subscribe, because this journey will take us farther than any human has ever traveled. Are we alone in the universe? The answer might be waiting on one of these incredible worlds. Prepare yourselves. We begin. Picture a cosmic recipe for life, and you need just 3 ingredients. But getting them right determines whether a world becomes a paradise or a hellscape. The first ingredient seems simple: liquid water. But here's where it gets tricky. Water only stays liquid in what scientists call the Goldilocks zone, that perfect distance from a star where temperatures hover between 32 and 212 degrees Fahrenheit. Too close to the star, and your oceans boil away into space like steam from a kettle. Too far away, and everything freezes solid, turning your world into a cosmic ice ball. Earth sits right in this sweet spot, about 93 million miles from our sun, where water can exist as liquid, ice, and vapor all at the same time. The second ingredient is an atmosphere. But not just any atmosphere will do. You need the right mix of gases to trap heat like a blanket while still allowing light to reach the surface. Think of it like wrapping yourself in a perfect winter coat, thick enough to keep you warm, but not so thick that you overheat. Venus has an atmosphere, but it's so dense with carbon dioxide that the surface temperature reaches 900 degrees Fahrenheit, hot enough to melt lead. The third ingredient might surprise you: a magnetic field. Without this invisible shield, deadly radiation from space strips away the atmosphere molecule by molecule. Mars once had flowing rivers, and maybe even oceans, but when its magnetic field died, the solar wind slowly stole its air away, leaving behind the frozen desert we see today. Here's what makes this recipe so rare. All 3 ingredients must work together perfectly for millions, even billions of years. A planet needs a stable orbit that doesn't swing too close or drift too far from its star. It needs the right size to hold onto its atmosphere, but not so big that it becomes a gas giant like Jupiter. The star itself must be calm enough not to blast the planet with deadly flares, yet active enough to provide steady energy. Scientists have discovered over 5,000 planets orbiting other stars, but fewer than 50 sit in that perfect zone where all 3 ingredients might exist together. Each one represents a potential second Earth, a world where alien skies might shelter alien seas, and where the chemistry of life could be writing its own story right now. The challenge becomes finding these needle-in-a-haystack worlds across the vast darkness of space, then figuring out which ones actually have the right conditions brewing beneath their clouds. We've built space telescopes that can detect the faintest dimming of starlight when a planet passes in front of its sun, measuring worlds so distant that their light takes years to reach us. But among all these distant possibilities, one planet stands out as our closest neighbor in the search for life. Just over 4 light-years away, a world orbits the nearest star to our own solar system, and the data suggests something extraordinary might be happening there. In 2016, astronomers detected something that changed everything: a planet just 0.2 times larger than Earth, circling the closest star to our solar system every 11 days. Proxima Centauri b sits 4.2 light-years away, which means if you could travel at the speed of light, you'd still need over 4 years to reach this world that might harbor the closest alien life to Earth. Here's what makes this discovery so stunning. This planet orbits directly in its star's habitable zone, where temperatures could allow liquid water to exist on the surface. But Proxima Centauri isn't like our Sun. It's a red dwarf star, smaller and cooler, glowing with a dim reddish light that would make noon on this world look like twilight on Earth. The planet faces a challenge that would terrify any astronaut. Proxima Centauri b is tidally locked to its star, meaning one side experiences eternal day, while the other side freezes in permanent night. Imagine standing on the border between these two extremes, where the sun hangs motionless in the sky like a dim red eye, never rising or setting, while behind you stretches an endless frozen wasteland under alien stars. Temperatures on the day side could reach 140 degrees Fahrenheit, while the night side plunges to minus 40 degrees. But here's where it gets interesting. If this world has an atmosphere thick enough to move heat around, the border zone between day and night might maintain temperatures perfect for liquid water. Scientists call this the Terminator line, and it could be where life makes its stand. The real mystery lies beneath the surface. Computer models suggest that if Proxima Centauri b has even a thin atmosphere, wind patterns could create a surprisingly stable climate. Hot air would rise on the day side, flow toward the night side, cool down, and return in a massive circulation pattern that could keep the entire planet at livable temperatures. Recent observations hint at something even more exciting. This world might have a magnetic field strong enough to protect it from its star's violent outbursts. Proxima Centauri occasionally erupts with solar flares 10 times more powerful than anything our sun produces, blasting its planet with deadly radiation. Without protection, these flares would strip away any atmosphere in just a few million years. But if Proxima Centauri b has held onto its air for the 4.8 billion years since the star system formed, that suggests something remarkable is happening there. The planet might have oceans, weather patterns, maybe even seasons, as its slightly elliptical orbit brings it closer and farther from its star. The distance to this world presents both opportunity and frustration. 4.2 light-years sounds close in cosmic terms, but it represents 25 trillion miles of empty space. Our fastest spacecraft would take over 70,000 years to reach Proxima Centauri b, yet it's so nearby that powerful future telescopes might actually photograph its surface and analyze its atmosphere for signs of life. But this single world is just the beginning of our journey through the cosmos. Deeper in space, an entire system of 7 planets waits, each one roughly Earth-sized, locked in a gravitational dance around a star so small and cool that all 7 worlds huddle closer to their sun than Mercury does to ours. 39 light-years from Earth, 7 worlds orbit so close to each other that if you stood on one planet's surface, the others would appear larger in your sky than our moon appears to us. The TRAPPIST-1 system packs these 7 Earth-sized planets into a space smaller than the distance between our sun and Mercury, creating a cosmic dance where each world's gravity tugs on its neighbors in perfect mathematical harmony. This star system operates like nothing we see in our solar system. TRAPPIST-1 itself is what astronomers call an ultra-cool dwarf star, so small and dim that you could fit 12 of them inside our sun. It burns hydrogen so slowly that it will keep shining for trillions of years, long after our sun swells into a red giant and dies. The star's faint reddish glow means all 7 planets orbit within what would be the habitable zone around a normal star. Here's where the system gets weird. These planets are locked in what scientists call orbital resonance, meaning their orbits sync up like clockwork. For every 8 times the innermost planet completes an orbit, the next planet orbits 5 times, and the pattern continues outward through the entire system. It's as if some cosmic engineer designed this system to stay stable for billions of years. The 3 planets in the middle of this chain, designated TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, sit squarely in the zone where liquid water could exist on their surfaces. But each world faces the same challenge as Proxima Centauri b. They're tidally locked, with one side always facing their star, while the other side freezes in permanent darkness. Scientists have used the Hubble Space Telescope and the James Webb Space Telescope to peer through these planets' atmospheres as they pass in front of their star. The data reveals something intriguing. At least 3 of these worlds might have substantial atmospheres, and one shows possible signs of water vapor floating in its air. The real mystery centers on TRAPPIST-1e, the fourth planet from the star. This world receives almost exactly the same amount of energy from its sun as Earth receives from ours, making it potentially the most Earth-like planet we've discovered. Computer models suggest it could have a thick atmosphere that distributes heat around the planet, creating moderate temperatures even on the permanently dark side. If you could visit TRAPPIST-1e, the experience would be unlike anything on Earth. The star would appear about 3 times larger in the sky than our sun, glowing with a deep red light that would make the landscape look like it's lit by firelight. The other 6 planets would hang in the sky like jewels, some showing crescents, others appearing as full disks, their positions changing as they orbit in their cosmic clockwork. The gravitational interactions between these 7 worlds create another possibility that excites scientists: tidal heating. As each planet's orbit gets stretched and squeezed by its neighbor's gravity, the resulting friction could warm the interiors enough to keep underground oceans liquid, even on worlds that seem too cold on the surface. Recent atmospheric analysis has revealed that these planets contain different amounts of water, suggesting each world tells its own story of formation and evolution. Some might be water worlds with deep oceans, while others could be rocky desert planets or ice-covered moons with hidden seas. But among all the worlds we've discovered, one planet stands out as Earth's closest twin, orbiting a star so similar to our Sun that scientists nicknamed it Earth's older cousin. 1,400 light-years away, a planet takes 385 days to complete one orbit around a star, almost identical to our Sun, creating seasons and a year length so close to Earth's that you could use the same calendar. Kepler 452 orbits within its star's habitable zone at just the right distance for liquid water, and this world has been doing so for 6 billion years, 1.5 billion years longer than Earth has existed. Here's what makes this planet extraordinary. Its star, Kepler 452, burns with almost the same temperature and brightness as our Sun, providing steady, stable energy that could support complex life for billions of years. The planet itself measures about 1.6 times Earth's diameter, making it what scientists call a super-Earth, large enough to have a thicker atmosphere that could trap heat and protect the surface from radiation. The gravity on Kepler 452 would feel about twice as strong as Earth's gravity, meaning if you weigh 150 pounds here, you'd weigh around 300 pounds there. Your muscles would adapt over time, but jumping or climbing would require much more effort. The stronger gravity also means this world could hold onto a thicker atmosphere for longer periods, potentially creating more stable weather patterns than Earth experiences. This planet's year lasts just 20 days longer than an Earth year, and its orbit sits in nearly the same position relative to its star as Earth sits relative to our Sun. If Kepler 452 has seasons, they would follow a familiar pattern: spring, summer, fall, and winter, lasting roughly the same length as Earth's seasons. Trees, if they exist there, might show growth rings similar to Earth trees. The age of this system raises fascinating questions about what might have evolved there. Earth's most complex life forms have only existed for a few 100 million years, but Kepler 452 has had 6 billion years to develop life. If biology took hold on this world early in its history, we might be looking at a planet where evolution has had 50% more time to create incredible diversity and complexity. Computer models suggest that if Kepler 452 started with the same amount of water as Earth, it might have developed into an ocean world with small continents scattered across its surface. The stronger gravity would create more dramatic tidal effects, potentially leading to larger tidal pools where early life could have gained a foothold before spreading to the oceans. The star Kepler 452 is about 1.5 billion years older than our Sun and burns slightly brighter, meaning this planet receives about 10% more energy than Earth receives. This extra energy could drive more active weather patterns, stronger storms, more evaporation, and more dramatic cloud formations that might be visible from space as swirling white patterns against blue oceans. Recent analysis of this system suggests something even more intriguing. As Kepler 452 ages, it gradually grows brighter and hotter, just like our Sun will do in the future. Kepler 452 might be showing us what Earth will look like in about 1 billion years, when our sun's increasing brightness begins to boil away our oceans and make our planet uninhabitable. If this world has developed life over its 6 billion year history, that life now faces the same challenge Earth will face in the future, adapting to a gradually warming planet as its star grows more luminous. The solutions life finds on Kepler 452b might teach us how future Earth organisms could survive similar changes. But while Kepler 452 offers a glimpse into Earth's possible future, another recently discovered world provides hope for finding life much closer to home, just 137 light-years away. A planet 1.5 times Earth's size completes an orbit around its star every 19 days, positioned precisely in the zone where liquid water could exist on its surface. TOI 715b represents one of the most recent additions to our catalog of potentially habitable worlds, discovered in late 2023 using NASA's Transiting Exoplanet Survey satellite. This world orbits a red dwarf star called TOI 715, much smaller and cooler than our Sun, which means the planet must huddle close to receive enough warmth for liquid water. The 19-day orbit places TOI 715b at roughly the same distance from its star as Mercury sits from our Sun, but because its star burns so much cooler, the planet receives just the right amount of energy to maintain moderate temperatures. Here's what makes this discovery particularly exciting. TOI 715b sits right in the middle of what astronomers call the conservative habitable zone, the region where scientists feel most confident that liquid water could exist. Many potentially habitable planets orbit at the edges of this zone, where small changes in atmospheric conditions could tip them toward freezing or boiling. TOI 715b has no such uncertainty. The planet's size suggests it could be a super-Earth with a substantial atmosphere, possibly thick enough to distribute heat around the planet and create a greenhouse effect that keeps temperatures stable. Computer models indicate that if this world has an atmosphere similar to Earth's but 2 to 3 times thicker, it could maintain liquid water even on its night side. Because TOI 715b orbits so close to Earth in cosmic terms, it represents an ideal target for atmospheric analysis using our most powerful telescopes. The James Webb Space Telescope can detect the chemical fingerprints of gases in this planet's atmosphere as it passes in front of its star, potentially revealing whether water vapor, oxygen, or other signs of biological activity exist in its air. The star, TOI 715, presents both advantages and challenges for life. Red dwarf stars burn for trillions of years, providing stable energy for much longer than stars like our Sun. However, they tend to produce violent flares during their youth that could strip away planetary atmospheres. At 5 billion years old, TOI 715 has settled into a calmer phase, making it more likely that its planet has retained whatever atmosphere it started with. Recent observations suggest that TOI 715b might not be alone. Scientists have detected hints of a second planet in this system, potentially even more Earth-like than the first. If confirmed, this would make TOI 715 one of the closest systems with multiple potentially habitable worlds, offering a unique laboratory for studying how planets in the same system can develop different characteristics. The planet's rapid 19-day orbit creates an interesting consequence. If TOI 715b has seasons, they would change incredibly quickly by Earth standards. Seasonal variations might last just a few days, creating rapidly shifting weather patterns that could challenge any life forms trying to adapt to changing conditions. Temperature variations across the planet's surface could create diverse climate zones within a relatively small area. The equatorial regions might stay warm enough for liquid water year-round, while polar regions could remain frozen, creating ice caps that advance and retreat with the planet's quick seasonal changes. For astronomers, TOI 715b represents something precious, a nearby laboratory where we can test our theories about habitability and atmospheric evolution. Its proximity means we might be able to detect radio signals if intelligent life exists there, and future space telescopes could potentially photograph its surface in enough detail to identify continents, oceans, and weather patterns. But while TOI 715b offers hope for finding life relatively close to home, another world farther out in space has already provided us with something extraordinary. The first confirmed detection of water vapor in a potentially habitable planet's atmosphere. 124 light-years from Earth, a planet 8 times more massive than our world orbits through its star's habitable zone, and in 2019, the Hubble Space Telescope detected something that sent shockwaves through the scientific community. Water vapor floating in its atmosphere. K218b became the first potentially habitable exoplanet, where we confirmed the presence of water in the air, transforming it from just another distant world into a place where the chemistry of life might actually be happening. This discovery marked a turning point in our search for life beyond Earth. For decades, scientists could only speculate about what might exist in the atmospheres of distant planets. But K218b provided the first direct evidence that worlds in habitable zones can indeed harbor water vapor, one of the key ingredients for life as we know it. The planet presents a puzzle that challenges our understanding of habitability. K218b is what scientists call a mini-Neptune, larger than Earth but smaller than Neptune, with a substantial atmosphere that might be mostly hydrogen and helium. Traditional models suggested such worlds couldn't support liquid water on their surfaces because their thick atmospheres would create runaway greenhouse effects, making them too hot for life. However, recent computer simulations reveal a surprising possibility. If K218b has the right atmospheric composition, with enough water vapor and other greenhouse gases, it might maintain moderate temperatures despite its size. The planet could even have liquid water clouds floating in its atmosphere, creating aerial oceans suspended in the sky like floating seas. The water vapor detection came from a technique called transmission spectroscopy, where scientists analyze starlight filtering through the planet's atmosphere as it passes in front of its star. Different gases absorb specific wavelengths of light, creating fingerprints that reveal the atmospheric composition. The water vapor signal from K218b was unmistakable. Hydrogen and oxygen bonded together in the exact proportions that create water. K218b completes one orbit around its star every 33 days, positioning it squarely in the habitable zone where liquid water could exist. The star, K218, is a red dwarf about half the size of our Sun, providing steady energy for potentially billions of years. The planet receives about the same amount of energy from its star as Earth receives from our Sun, suggesting moderate surface temperatures. Here's where the story gets even more intriguing. In 2023, the James Webb Space Telescope took another look at K218b and detected possible signs of other atmospheric gases, including carbon dioxide and possibly even hydrogen sulfide or other sulfur compounds. These gases could indicate active geological processes or, more exciting, biological activity. The planet's substantial mass creates gravity about 2.3 times stronger than Earth's, which would significantly affect how any atmosphere and weather systems behave. Stronger gravity would create denser air at the surface and might allow for more massive cloud formations and more intense weather patterns than we see on Earth. If K218b has a solid surface beneath its thick atmosphere, that surface might be completely covered by water, creating a world-spanning ocean. The high pressure from the thick atmosphere could allow water to remain liquid at higher temperatures than on Earth, potentially creating a hot, humid environment that could still support certain types of life. The detection of water vapor on K218b opened up new possibilities for finding life in our galaxy. It proved that our telescopes can detect biosignature gases in the atmospheres of distant worlds, bringing us one step closer to answering whether we're alone in the universe. Scientists now use K218b as a prototype for studying atmospheric chemistry on potentially habitable worlds. Each new observation teaches us more about how atmospheres behave on planets very different from Earth, expanding our definition of what makes a world suitable for life. But while K218b showed us water floating in alien skies, our next destination takes us to an even stranger world, a planet locked in eternal twilight, where one side burns under a red sun that never sets, while the other side freezes under stars that never fade. 23 light-years away, a planet slightly larger than Earth experiences a phenomenon that would transform human civilization. One hemisphere basks in eternal daylight under a red dwarf sun, while the other hemisphere freezes in permanent night under alien constellations. Gliese 667 cc is tidally locked to its star, creating a world where the sun never rises or sets, hanging motionless in the sky like a crimson eye that never blinks. This planet orbits its star every 28 days, at a distance closer than Mercury orbits our sun, but its star burns so cool and dim that Gliese 667 cc receives just the right amount of energy for liquid water to exist on its surface. The result is a world divided into 3 distinct climate zones that could each harbor completely different forms of life. The day side of Gliese 667 cc experiences constant illumination under a sun that appears about twice as large as our sun looks from Earth, glowing with a deep red light that would make familiar landscapes appear alien and mysterious. Temperatures on this hemisphere could reach 130 degrees Fahrenheit, creating vast deserts where any surface water would evaporate quickly. But underground aquifers might provide oases where life could flourish. The night side tells a different story entirely. Here, temperatures plunge to -80 degrees Fahrenheit or lower, cold enough to freeze carbon dioxide out of the atmosphere and create dry ice snow. But this frozen hemisphere would offer spectacular views of the cosmos. With no sun to wash out the sky, the stars would shine with crystal clarity, and any moons orbiting Gliese 667 cc would cast shadows and create tides on this eternally dark hemisphere. Between these two extremes lies the most fascinating region of all, the Terminator Zone, the narrow band where day meets night in perpetual twilight. Here, the red sun hangs just at the horizon, painting the landscape in shades of orange and crimson while temperatures hover near the freezing point of water. This twilight zone could be where liquid water persists, where weather patterns create clouds and storms, and where life might find its most comfortable home. Computer models suggest that if Gliese 667 cc has an atmosphere thick enough to move heat around the planet, powerful wind systems would develop between the hot day side and cold night side. Hot air would rise from the sunlit hemisphere, flow toward the dark side at high altitude, cool and sink, then return to the day side at ground level, creating massive circulation patterns that could moderate temperatures across the entire planet. The planet's gravity is about 4.5 times stronger than Earth's, which would create several interesting effects. The thicker atmosphere this allows could trap more heat and create more dramatic weather patterns. Raindrops would fall faster and hit harder, winds would feel more powerful, and the increased atmospheric pressure might allow water to remain liquid at higher temperatures. The red dwarf star Gliese 667c presents both opportunities and challenges for life. Red dwarfs burn for trillions of years, providing stable energy far longer than stars like our Sun. However, they tend to produce violent flares, especially when they're young. Gliese 667c has settled into a relatively calm phase, but occasional flares could still bombard the planet with radiation. If intelligent life evolved on Gliese 667cc, their civilization would develop in ways completely alien to human experience. They might build cities in the Terminator Zone where temperatures stay moderate, using the temperature differences between day and night sides to generate energy. Their calendar would be based on orbital periods rather than day-night cycles, and they would never experience sunrise or sunset. The permanent twilight zone could create unique evolutionary pressures that produce life forms unlike anything on Earth. Plants might evolve to capture the dim red light efficiently, developing black or deep purple leaves instead of green ones. Animals might develop enhanced night vision to navigate the perpetual twilight, or they might rely more heavily on other senses like hearing or touch. But compared to the strange seasonal patterns on our next destination, even permanent twilight might seem normal. Farther out in space, a super-Earth experiences seasons that last longer than most animals live on Earth. 42 light-years from Earth, a world 7 times more massive than our planet takes 200 days to complete one orbit around its star, But here's where it gets strange. The planet's tilted axis creates seasons that last 25 Earth years each, long enough for human generations to be born, live their entire lives, and die during a single spring. HD 40,370 Hey challenges our understanding of how seasonal changes affect life and climate on a planetary scale. This super-Earth orbits at the outer edge of its star's habitable zone, receiving just enough energy to potentially maintain liquid water on its surface. The star, HD 40,307, burns slightly cooler and dimmer than our Sun, which means the planet must complete its orbit in the sweet spot where temperatures hover right around the freezing point of water. Small changes in the planet's distance from its star during its slightly elliptical orbit could mean the difference between a world covered in ice and one with flowing rivers. The planet's massive size creates gravity about 2.4 times stronger than Earth's, which has profound implications for its atmosphere and weather patterns. The stronger gravity allows HD 40,307 Grang to hold on to a much thicker atmosphere than Earth possesses, potentially creating a greenhouse effect that keeps the planet warm enough for liquid water even at its distant orbit. Here's where the decades-long seasons create a unique situation. As the planet's tilted axis points different hemispheres toward the star during its 200-day orbit, one hemisphere experiences 25 years of summer, while the other endures 25 years of winter. The temperature differences between these hemispheres would create weather patterns, unlike anything on Earth. Massive storm systems that could rage for years, migrating between hemispheres as the seasons slowly change. The long seasonal cycles would create opportunities for life that don't exist on Earth. Plants could evolve to take advantage of the decades-long growing seasons, potentially reaching enormous sizes during the 25-year summers. Forests might develop that grow for decades, then enter dormancy for decades, creating landscapes that transform completely over the course of a century. Animal life would face unique challenges on HD 40,307G. Species might evolve migration patterns that span entire generations, with offspring following routes their parents never completed. Some animals might evolve extended lifespans to survive the long winters, while others might develop extreme hibernation strategies that last for decades. The thick atmosphere created by the planet's strong gravity could lead to weather phenomena that dwarf anything on Earth. Hurricane-like storms might persist for years at a time, and the atmospheric pressure at sea level could be several times higher than Earth's, allowing liquid water to exist at temperatures well above 212 degrees Fahrenheit. Computer models suggest that HD 40,307 Grang might have a very active geological system due to its large size and mass. The planet's interior would generate more heat than Earth's core, potentially leading to more volcanic activity and more dramatic mountain-building processes. The landscape might change significantly even within the lifetime of long-lived organisms. The planet's position at the outer edge of the habitable zone means that it might experience periods where its entire surface freezes during the global winter season, only to thaw completely during global summer. This creates the possibility of a world where ice ages and warm periods alternate every 50 years in a predictable cycle. If HD 40,307 Jing has moons, they would experience even more extreme seasonal variations as they orbit a planet that itself goes through decades-long seasons. The gravitational interactions between the planet and its moons could create tidal heating that keeps liquid water available even during the longest winters. The implications for any civilization that might evolve on HD 40,307 Grang are staggering. Their technology and culture would need to account for climate changes that span multiple generations. They might develop advanced, long-term planning capabilities that far exceed anything humans have achieved, building infrastructure designed to last through decades of winter or planning agricultural strategies that account for 25-year growing seasons. But while HD 40,307 Grang shows us how extreme seasonal variations might affect life, our next destination takes us to an even more challenging world, a planet so far from its star that it should be frozen solid, yet might harbor liquid water in hidden underground oceans. 1,194 light-years away, A planet just over one-third larger than Earth orbits at the very outer edge of its star's habitable zone, where surface temperatures likely hover around -50 degrees Fahrenheit year-round. Kepler 442 should be a frozen wasteland, yet scientists believe this distant world might harbor vast underground oceans, kept liquid by the planet's own internal heat, creating a hidden biosphere that could support life in perpetual darkness. This world completes one orbit around its star every 112 days, placing it at roughly the same distance from its sun as Venus sits from ours. However, Kepler 442's star burns much cooler and dimmer than our sun, providing only about 70% of the energy that Earth receives. The result is a planet where any surface water would freeze solid, creating ice sheets that could extend from pole to pole. The planet's size holds the key to its potential habitability. Kepler 442 contains about twice as much mass as Earth, creating stronger gravity that helps the planet retain a thick atmosphere. This atmospheric blanket could trap enough heat to prevent the planet from becoming completely frozen, and more importantly, the extra mass means the planet's interior stays hot for billions of years longer than smaller worlds. Here's where the hidden ocean theory becomes compelling. The decay of radioactive elements in Kepler 442's core, combined with tidal heating from its slightly elliptical orbit, could generate enough internal heat to melt ice at depths of just a few miles below the surface. Computer models suggest that beneath the frozen crust, this world might harbor liquid water oceans deeper than any ocean on Earth. These subsurface oceans would exist in complete darkness, warmed from below by geothermal vents that could provide energy for life. On Earth, we've discovered thriving ecosystems around deep ocean volcanic vents where sunlight never penetrates. Creatures in these environments derive energy from chemical processes rather than photosynthesis, creating food chains based on bacteria that convert sulfur compounds and other chemicals into usable energy. Kepler 442 might harbor similar ecosystems on a planetary scale. The interface between the liquid ocean and the rocky seafloor could host countless hydrothermal vents, creating chemical gardens where exotic life forms evolve in ways completely independent of surface conditions. These organisms might never know that a star exists, living their entire existence in the warm, dark water beneath miles of ice. The planet's thick atmosphere could create another surprising possibility. Even though surface temperatures stay well below freezing, atmospheric pressure might be high enough to allow liquid water to exist in deep valleys or crater basins, creating isolated pockets where surface life could survive. These areas would be like oases in a frozen desert, connected to the vast underground oceans through cracks and caves in the ice. The long orbital period means that Kepler 442 experiences seasons that last about 28 Earth days each. While these seasonal changes wouldn't be dramatic enough to melt the surface ice, they could create thermal cycles that pump liquid water up and down through the planet's crust, mixing nutrients between the surface and the deep oceans. If life exists in Kepler 442's hidden oceans, it might be incredibly diverse and sophisticated. With billions of years to evolve in a stable, protected environment, these organisms could develop complex ecosystems that dwarf anything we see on Earth. The constant darkness would favor life forms that communicate through sound, chemical signals, or even electrical discharges rather than visual displays. The planet's strong gravity would create unique conditions for any life that did evolve there. Organisms would need to be more robust to survive the increased pressure, and any creatures that evolved gas-filled swim bladders would need much stronger structures to maintain buoyancy in the high-gravity environment. Recent advances in telescope technology might soon allow us to detect signs of these hidden biospheres. If Kepler 442's underground oceans occasionally vent water vapor or other gases through cracks in the ice, space telescopes could detect these atmospheric signatures and confirm the presence of subsurface water. But while Kepler 442b might hide its oceans beneath ice, our next destination faces a completely different challenge: surviving the violent radiation storms from a star that regularly blasts its planet with deadly energy. Just 13.8 light-years from Earth, a rocky planet 4 times more massive than our world orbits dangerously close to a red dwarf star, that unleashes violent radiation storms powerful enough to strip away atmospheres and sterilize surfaces. Wolf 1061 sits right on the inner edge of its star's habitable zone, where liquid water could theoretically exist. But the planet faces a constant battle against stellar winds and flares that would make survival an extraordinary challenge for any life forms brave enough to call this world home. This super-Earth completes one orbit around its star every 17.9 days, racing through space at speeds that would make Mercury look sluggish. The close orbit places Wolf 1061 at roughly 1/20th the distance between Earth and our Sun, so close that the star would appear 25 times larger in the sky than our Sun appears from Earth, dominating the horizon like a massive red wall of fire. Wolf 1061, the star at the center of this system, exemplifies the dark side of red dwarf stars. While these small stars burn for trillions of years and seem ideal for supporting long-term biological evolution, they tend to be magnetically active, producing stellar flares that can increase their brightness by 10 times or more in a matter of minutes. When these flares strike Wolf 1061 they bombard the planet with X-rays and ultraviolet radiation intense enough to break apart water molecules in the atmosphere. The planet's substantial mass works both for and against its prospects for habitability. The stronger gravity helps Wolf 1061 hold on to whatever atmosphere it possesses, but it also means that any atmosphere would be denser and potentially more vulnerable to chemical breakdown by radiation. Recent computer models suggest that if this world started with an Earth-like atmosphere, it might have lost most of its water vapor and oxygen to space over the past few billion years. Here's where the story gets interesting. Wolf 1061 might represent a planet in transition, a world that once had oceans and a thick atmosphere but is slowly losing both to the relentless assault of stellar radiation. If this process is happening gradually, the planet might still harbor liquid water in protected regions, like deep valleys or underground caverns where the atmosphere remains thick enough to maintain stable conditions. The planet's rapid orbit creates another unique situation. The 17.9-day year means that seasonal changes, if they exist, would flash by in a matter of Earth days. Any life forms that evolved on Wolf 1061 would need to adapt to incredibly rapid environmental cycles, or they would need to find stable niches that don't change with the planet's quick orbit. Scientists have used computer simulations to explore what might happen to water on Wolf 1061 during the most violent stellar flares. The models suggest that while the planet's day side faces the full force of the radiation storms, water on the night side might survive in a perpetual freeze-thaw cycle. As the planet rotates, ice on the night side melts when it rotates into daylight, creating temporary rivers and lakes that freeze again when they rotate back into darkness. The magnetic field strength of Wolf 1061 could determine whether this world has any chance of supporting life. Earth's magnetic field deflects most of the dangerous radiation from our Sun, but Wolf 1061 faces a much more violent stellar environment. If the planet has a strong magnetic field generated by its iron core, it might be able to create a protective bubble that shields at least part of its surface from the worst radiation storms. Recent observations suggest that Wolf 1061 might not be completely airless. Spectroscopic analysis hints that the planet might still retain a thin atmosphere, possibly composed of heavier gases that resist being stripped away by stellar winds. Carbon dioxide, water vapor, and nitrogen could persist in this thin atmosphere, creating surface pressures just high enough to allow liquid water to exist in deep basins. The planet's proximity to Earth makes it an ideal target for detailed study. Future space telescopes will be able to analyze Wolf 1061's atmosphere in real time, watching how it responds to stellar flares and measuring whether water vapor appears and disappears as the planet rotates. These observations could teach us how planetary atmospheres evolve around active stars. If life does exist on Wolf 1061, it would need to be incredibly resilient. Organisms might evolve to live underground, emerging only during calm periods between stellar storms. They might develop sophisticated DNA repair mechanisms to fix radiation damage, or they might evolve to use the high-energy radiation as a source of energy rather than seeing it as a threat. But while Wolf 1061X shows us how life might survive in a hostile radiation environment, our journey now takes us to a calmer world where the challenges are more subtle and the possibilities for life even more intriguing. 41 light-years from Earth, a planet nearly 7 times more massive than our world orbits a quiet red dwarf star every 25 days, and recent observations suggest something remarkable. This dense, rocky super-Earth might have managed to hold onto a substantial atmosphere despite billions of years of stellar radiation. LHS 1140b represents a success story in planetary survival, a world that appears to have won the battle against atmospheric erosion that destroys so many other planets. This planet's extraordinary density sets it apart from other super-Earths we've discovered. LHS 1140b packs almost 7 Earth masses into a world only 1.7 times Earth's diameter, creating a density that suggests a composition of mostly iron and rock with very little water. The result is a planet with surface gravity about 5 times stronger than Earth's, where the atmospheric pressure at sea level could be 20 times higher than what we experience. The thick, high-pressure atmosphere creates possibilities that don't exist on lighter worlds. Water could remain liquid at temperatures up to 400 degrees Fahrenheit, allowing for hot springs and geysers that would instantly boil away on Earth. The dense air would make sound travel differently. Voices would sound deeper and carry farther, while the increased atmospheric pressure would make weather phenomena more intense and dramatic. LHS 1140b orbits well within its star's habitable zone, receiving about 43% of the energy that Earth gets from our Sun. However, the planet's thick atmosphere could trap enough heat through greenhouse effects to maintain moderate surface temperatures. Computer models suggest that if this world has the right mix of carbon dioxide and water vapor, it could support liquid water across most of its surface. The star LHS 1140 offers ideal conditions for supporting life over long time periods. This red dwarf burns steadily and calmly, producing far fewer dangerous flares than most stars of its type. The stable energy output means that LHS 1140b has experienced relatively consistent conditions for the billions of years since the system formed, giving any potential life plenty of time to evolve and diversify. Recent atmospheric analysis using the James Webb Space Telescope has detected possible signs of water vapor and other gases in LHS 1140b's atmosphere. The data suggests that this world might have weather patterns, clouds, and maybe even precipitation, all signs that active atmospheric circulation could be distributing heat and moisture around the planet. The planet's high density creates another intriguing possibility. The massive iron core would generate a powerful magnetic field that could protect the atmosphere from being stripped away by stellar winds. This magnetic shield might explain how LHS 1140b has managed to keep its atmosphere when so many other planets around red dwarf stars have lost theirs. If you could visit LHS 1140b, the experience would challenge every assumption about what a habitable world looks like. The 5 times stronger gravity would make every movement exhausting, but the thick atmosphere would create spectacular optical effects, deeper blue skies, more vivid sunsets, and clouds that could tower much higher than any formations on Earth. The dense atmosphere would also create unique opportunities for flight. The thick air would provide much more lift, potentially allowing large flying creatures to evolve even in the high-gravity environment. Aircraft designed for LHS 1140b could have much smaller wings while carrying heavier loads. The planet's 25-day orbit creates rapid seasonal changes that could drive evolution in unexpected directions. Life forms might develop to take advantage of these quick cycles, growing rapidly during favorable seasons and entering dormancy during challenging periods. But while LHS 1140b shows us how a dense world might maintain its atmosphere, our next destination reveals an even more Earth-like possibility, a planet so similar to our own that scientists call it Earth's twin. 300 light-years from Earth, a planet almost exactly Earth size orbits through its star's habitable zone every 19.5 days, receiving 95% of the energy that Earth gets from our Sun. Kepler 1649 represents the closest match to Earth's size and energy input that we've discovered, making it potentially the most Earth-like exoplanet in our catalog of distant worlds. This remarkable world measures just 1.06 times Earth's radius, making it so close to Earth's size that the difference would be barely noticeable to a human visitor. The similar size suggests that Kepler 1649 likely has similar surface gravity, atmospheric pressure, and geological processes to Earth, creating conditions where human-like life could potentially thrive without major adaptations. The planet orbits a red dwarf star called Kepler 1649, which burns much cooler and dimmer than our Sun. To receive nearly the same amount of energy as Earth, Kepler 1649K must orbit much closer to its star, completing one orbit in less than 20 Earth days. This close orbit means the planet is likely tidally locked, with one hemisphere experiencing eternal daylight while the other remains in permanent darkness. The energy balance on Kepler 1649 creates a fascinating scenario. Despite being tidally locked, the planet receives almost exactly the same total energy as Earth, just distributed differently across its surface. The day side might experience temperatures around 150 degrees Fahrenheit, while the night side could drop to minus 100 degrees. However, if the planet has an atmosphere thick enough to redistribute heat, the entire surface could maintain moderate temperatures. Recent computer models suggest that Kepler 1649 could have developed an atmosphere remarkably similar to Earth's. The planet's Earth-like size means it would have similar volcanic outgassing patterns and similar ability to retain atmospheric gases. If this world started with similar initial conditions to Earth, it might have evolved to have breathable air, liquid water oceans, and weather patterns that feel familiar to terrestrial life. The discovery of Kepler 1649 came from a detailed reanalysis of data from the now-retired Kepler Space Telescope. Scientists initially missed this planet because its transit signal was so similar to instrument noise. Only advanced computer algorithms and years of careful analysis revealed the regular dimming pattern that indicated a planet passing in front of its star. This near miss in discovery highlights how many Earth-like planets might be hiding in our existing data. Kepler 1649 suggests that Earth-sized planets in habitable zones might be much more common than we previously thought, hidden in the noise of stellar observations, waiting for better analysis techniques to reveal them. The star system itself offers clues about potential habitability. Kepler 1649 is about 75% of our Sun's mass and burns steadily without the violent flares that plague many red dwarf stars. The calm stellar environment means that Kepler 1649 has likely experienced stable conditions for billions of years, providing ample time for complex life to evolve. If Kepler 1649 has oceans, they would behave very similarly to Earth's oceans due to the similar gravity and energy input. Tides would follow familiar patterns. Ocean currents would develop in response to temperature differences between the day and night sides, and coastal regions could experience weather patterns that mirror Earth's tropical and temperate zones. The planet's rapid 19.5-day orbit creates an interesting calendar challenge. If intelligent life evolved on Kepler 1649, their concept of a year would be incredibly short by Earth standards. Seasonal changes, if they exist, would flash by in a matter of Earth weeks, potentially creating life forms that adapt to rapid environmental cycles. The similarity to Earth extends to potential geological activity. A planet with Earth's size and composition would likely have plate tectonics, volcanic activity, and mountain-building processes that constantly reshape the surface. These geological processes could create diverse landscapes and provide the chemical cycling necessary to support complex ecosystems. Kepler 1649 649T represents the holy grail of exoplanet discovery, a world so similar to Earth that it could potentially support not just life, but life as we know it. However, our next destination shows us that even planets with ideal conditions can face unexpected challenges that test the limits of survival. 730 light-years away, a planet slightly larger than Neptune orbits so close to its star that it completes one orbit every 18 hours, surviving in a region where temperatures reach 3,600 degrees Fahrenheit, hot enough to vaporize iron. TOI 849b represents one of the most extreme survival stories in our galaxy, a world that appears to have been partially swallowed by its star and lived to tell the tale. This extraordinary planet sits at a distance from its star where no planet should be able to exist. The intense radiation and stellar winds should have stripped away any atmosphere billions of years ago, yet TOI 849b persists, suggesting that this world has survived catastrophic events that would have destroyed most other planets. Scientists believe we might be looking at the naked core of what was once a much larger gas giant planet. The planet's 18-hour orbit creates the shortest year of any potentially habitable world we've discovered. Day and night cycles flash by so quickly that the planet exists in a state of constant transition, with temperatures varying dramatically as different regions rotate into and out of the star's intense radiation. The rapid rotation might actually help distribute heat around the planet, preventing any single region from becoming too hot to support exotic forms of life. Here's where the survival story becomes even more remarkable. Computer models suggest that TOI 849b might have started as a gas giant planet similar to Jupiter, with a massive atmosphere of hydrogen and helium surrounding a solid rocky core. As the star evolved and grew brighter, the planet's orbit decayed, bringing it closer and closer to the stellar surface until the outer atmosphere began to boil away into space. The process of atmospheric stripping might have taken hundreds of millions of years, gradually revealing the dense rocky core that we observe today. This core likely contains exotic materials forged under the extreme pressure of the original gas giant's atmosphere. Diamond layers, metallic hydrogen, and other materials that could only form under conditions impossible to recreate on Earth. TOI 849b's surface composition defies easy categorization. The temperatures are so extreme that many common materials exist in states we never see on Earth. Iron and nickel might form vast molten seas, while silicon compounds could create flowing glass rivers. The landscape would be alien beyond imagination, with mountains of crystallized carbon rising from plains of liquid metal. Despite the hellish conditions, scientists speculate that TOI 849b might harbor life in unexpected places. Deep beneath the surface, where temperatures drop to merely several hundred degrees, exotic biochemistry might utilize the abundant energy from radioactive decay and chemical reactions between different molten materials. These organisms would need to be based on completely different chemistry than Earth life, possibly using silicon or other heat-resistant materials instead of carbon. The planet's survival offers insights into planetary formation and evolution throughout the galaxy. If a world can endure being partially consumed by its star and still maintain its structural integrity, it suggests that planetary cores are much more resilient than we previously thought. TOI 849b might represent a new class of planets, stellar survivors that emerge from close encounters with their stars. The extreme conditions on TOI 849b create a natural laboratory for studying matter under conditions that we can't replicate in Earth-based experiments. The surface pressure, combined with temperatures that melt most materials, creates states of matter that exist nowhere else in our solar system. Studying this world could teach us about the interior conditions of gas giant planets and the behavior of materials under extreme conditions. Recent observations suggest that TOI 849b might have a thin atmosphere composed of vaporized rock and metal. Magnesium, silicon, and iron atoms float in the air as individual particles, creating an atmosphere unlike anything we've previously discovered. This metallic atmosphere might create spectacular visual effects, clouds that shine like mirrors and lightning that glows with the colors of different metals. The planet's proximity to its star means that it experiences tidal forces strong enough to flex the solid surface, generating additional heat through friction. This tidal heating might power geological activity that constantly resurfaces the planet, creating a world where the landscape changes dramatically over periods of just a few years. But while TOI 849b shows us how planets can survive the most extreme stellar encounters, our next destination takes us to a world facing a different kind of challenge: the delicate balance between habitability and catastrophic climate change. 31 light-years from Earth, a super-Earth twice our planet's size orbits at the outer edge of its star's habitable zone, where the delicate balance between ice and fire could determine whether this world becomes a paradise with flowing water or a hellscape with surface temperatures hot enough to melt lead. GJ 357d sits at the critical boundary where small changes in atmospheric composition could trigger runaway greenhouse effects that transform a potentially habitable planet into something resembling Venus. This planet completes one orbit around its red dwarf star every 55.7 days, positioning it at the very edge of the zone where liquid water could exist on its surface. Computer models suggest that GJ 357d receives about the same amount of energy from its star as Mars receives from our Sun, which should make it a frozen world, with surface temperatures well below the freezing point of water. However, the planet's larger size changes everything. GJ 357d contains about 6.1 times Earth's mass, creating gravity strong enough to hold onto a much thicker atmosphere than smaller planets can maintain. If this atmosphere contains even modest amounts of greenhouse gases like carbon dioxide or water vapor, the enhanced greenhouse effect could warm the planet enough to support liquid water across its entire surface. Here's where the story becomes a cautionary tale about planetary climate systems. The same atmospheric thickness that could make GJ 357d habitable also makes it vulnerable to runaway greenhouse warming. If too much water vapor enters the atmosphere, it could trap so much heat that the oceans begin to boil. Water vapor is itself a powerful greenhouse gas, so more evaporation leads to more warming, which leads to more evaporation, creating a feedback loop that could transform the planet into a steam-covered inferno. Scientists believe this runaway process might be happening on GJ 357d right now, or it might have happened billions of years ago when the planet was younger and received more energy from its star. Red dwarf stars like GJ 357 gradually grow brighter over time, meaning this planet might have started as a frozen world, warmed to habitability, and then continued warming until it became uninhabitable. The planet's 55-day orbit creates seasonal variations that could play a crucial role in its climate stability. As GJ 357d moves slightly closer and farther from its star during its elliptical orbit, the changing energy input could trigger seasonal climate shifts. If the planet sits right at the edge of runaway greenhouse conditions, these orbital variations might push it back and forth between habitable and uninhabitable states. Recent atmospheric modeling suggests that GJ 357d might exist in one of several possible climate states. In the best-case scenario, the planet has a thick but stable atmosphere that maintains surface temperatures between 32 and 100 degrees Fahrenheit, allowing for liquid water oceans and Earth-like weather patterns. In the worst-case scenario, runaway greenhouse warming has created surface temperatures exceeding 1,000 degrees Fahrenheit. The planet's strong gravity would create unique atmospheric dynamics regardless of its current climate state. Weather systems would be more intense than anything on Earth, with storms that could persist for weeks and wind patterns that redistribute heat around the planet with incredible efficiency. If GJ 357d has retained liquid water, its weather could include rainstorms of almost unimaginable intensity. The possibility of runaway greenhouse effects on GJ 357d makes it a crucial test case for understanding climate stability on exoplanets. Scientists use computer models of this world to explore how small changes in atmospheric composition can lead to dramatic climate shifts. These studies help us understand not only the fate of distant worlds, but also the long-term stability of Earth's own climate. If GJ 357d has already undergone runaway greenhouse warming, it might still harbor life in unexpected places. High in the atmosphere, where temperatures drop to more moderate levels, clouds of sulfuric acid could provide a habitat for airborne microorganisms, similar to what some scientists propose might exist in Venus's upper atmosphere. The planet's location, at the edge of habitability, makes it an ideal target for atmospheric studies using space telescopes. By analyzing the composition of GJ 357D's atmosphere, scientists can determine whether this world represents a cautionary tale of climate change or a success story of atmospheric stability. Recent observations hint that GJ 357D might have an atmosphere rich in carbon dioxide with traces of water vapor, suggesting that the planet sits right at the boundary between habitability and runaway greenhouse conditions. This precarious balance makes it one of the most scientifically valuable worlds for understanding how planetary climates evolve over billions of years. But while GJ 357D shows us the dangers of atmospheric instability, our next destination takes us back to a more familiar scenario, a world that might be showing us Earth's own future as our sun slowly grows brighter and warmer. 1,400 light-years away, we return to Earth's older cousin to witness something that should terrify and fascinate us in equal measure: a potentially habitable planet experiencing the same gradual warming that Earth will face in about 1 billion years, when our sun grows too bright and hot to support life. Kepler 452 orbits a star that's 1.5 billion years older than our sun, and this ancient system might be showing us exactly what happens when a once-perfect world begins the slow slide toward uninhabitability. The star Kepler 452 has been burning for about 6 billion years, compared to our sun's 4.6 billion year age, and during that extra time it has grown about 20% brighter and hotter. This increased luminosity means that Kepler 452 now receives about 10% more energy than Earth gets from our sun, enough additional heat to potentially trigger the early stages of runaway greenhouse warming that could boil away the planet's oceans. Here's what makes this scenario both tragic and inevitable. All sun-like stars gradually grow brighter as they age, burning their hydrogen fuel more efficiently over time. Kepler 452b might have enjoyed billions of years of perfect Earth-like conditions, with moderate temperatures, liquid water oceans, and stable weather patterns. But now, as its star enters middle age, those perfect conditions are slowly disappearing. Computer models of Kepler 452b's current climate suggest several possible scenarios. In the most optimistic case, the planet's atmosphere has adapted to the increased stellar energy by developing more reflective cloud cover that bounces extra heat back into space. White clouds and ice caps could act like mirrors, keeping the planet cool enough to maintain liquid water despite the brighter star. However, the more likely scenario paints a darker picture. The extra energy from the aging star has probably begun to evaporate more water from Kepler 452b's oceans, putting additional water vapor into the atmosphere. Since water vapor is a powerful greenhouse gas, this creates a feedback loop where more evaporation leads to more warming, which leads to even more evaporation. The planet's larger size might actually make this process worse. Kepler 452b has about 60% more mass than Earth, creating stronger gravity that allows it to hold onto a thicker atmosphere. While this was probably beneficial when the planet was younger, the thicker atmosphere now traps more heat, accelerating the greenhouse warming process. If Kepler 452 has already entered the runaway greenhouse phase, its surface might now experience temperatures hot enough to melt zinc, with atmospheric pressure dozens of times higher than Earth's. The oceans that once supported life would have boiled away billions of years ago, leaving behind a hellish world shrouded in thick clouds of steam and carbon dioxide. But there's another possibility that offers hope for life's persistence. Some scientists propose that as Kepler 452b's surface became uninhabitable, life might have migrated upward into the planet's atmosphere. High-altitude regions where temperatures remain moderate could harbor floating ecosystems of airborne microorganisms that never touch the scorching surface below. The planet's thick atmosphere might also create opportunities for life in unexpected places. Deep underground, where the surface heat can't penetrate, extensive cave systems could maintain moderate temperatures and host ecosystems based on geothermal energy rather than sunlight. These subterranean biospheres could persist for billions of years, completely isolated from the hostile surface conditions. Studying Kepler 452 helps scientists understand Earth's own future. In about 1 billion years, our sun will grow bright enough to trigger the same runaway greenhouse effect on Earth. The oceans will boil away. The atmosphere will become unbreathably thick, and surface temperatures will rise to levels that would kill any known life form. However, this distant catastrophe also represents an opportunity. By the time Earth faces these conditions, human technology might be advanced enough to move our planet to a more distant orbit, or to construct massive solar shields that reduce the amount of energy reaching Earth's surface. Alternatively, we might have developed the ability to terraform other worlds, or to survive in space habitats completely independent of planetary surfaces. The story of Kepler 452 reminds us that habitability is not permanent. Even perfect worlds eventually become uninhabitable as their stars evolve, but life has billions of years to adapt to these slow changes. The question is whether intelligence evolves quickly enough to find technological solutions to cosmic-scale problems. But while Kepler 452 shows us the challenges of stellar aging, our next destination brings us back to the excitement of recent discovery, a world that astronomers found just months ago, adding new possibilities to our growing catalog of potentially habitable planets. 105 light-years from Earth, astronomers in late 2022 discovered something that immediately captured the attention of planet hunters worldwide, a super-Earth 1.4 times our planet's size, orbiting squarely in its star's habitable zone where liquid water could flow across its surface. LP 899c represents one of the most promising recent additions to our catalog of potentially habitable worlds, a planet so well positioned for life that scientists have already begun planning detailed atmospheric studies. This newly discovered world completes one orbit around its red dwarf star every 8.8 days, positioning it at the perfect distance to receive energy levels similar to what Earth gets from our Sun. The star LP 899 burns cooler and dimmer than our Sun, which means the planet must orbit much closer to stay warm, but the energy balance works out almost perfectly for maintaining liquid water on the surface. The rapid 8.8-day orbit creates a year shorter than most Earth vacations, but this quick orbital period actually helped astronomers discover the planet. LP 899c transits in front of its star so frequently that scientists could observe multiple transits within just a few weeks, confirming the planet's existence and measuring its size with high precision. The planet's size suggests it could be a rocky world with a substantial atmosphere, possibly thick enough to redistribute heat around the planet and maintain moderate temperatures even if it's tidally locked to its star. Computer models indicate that LP 899c could have surface conditions ranging from pleasantly Earth-like to dramatically alien, depending on its atmospheric composition and geological activity. What makes this discovery particularly exciting is the timing. LP 899c was found using data from the Transiting Exoplanet Survey Satellite, TESS, which has revolutionized our ability to find planets around nearby stars. The planet is close enough to Earth that the James Webb Space Telescope can analyze its atmosphere in detail, potentially detecting water vapor, oxygen, or other signs of biological activity. The star LP 899 offers ideal conditions for supporting life over long time periods. This red dwarf star burns steadily without the violent flares that make many similar stars dangerous to planetary atmospheres. The calm stellar environment means that LP 899c has likely experienced stable conditions for billions of years, providing ample time for life to evolve and diversify. Recent follow-up observations have revealed intriguing hints about the planet's characteristics. Measurements of how much starlight the planet blocks during transit suggest that LP 899c might have a thick atmosphere that extends well above its solid surface. This atmospheric halo could indicate the presence of water vapor, carbon dioxide or other gases that could support habitability. The planet's position in its star's habitable zone is so favorable that some scientists have proposed it as a prime target for more intensive study. Ground-based telescopes are already monitoring LP 899c for signs of atmospheric variations that could indicate weather patterns, seasonal changes, or other dynamic processes on the planet's surface. If LP 899c has oceans, they would experience unique tidal effects due to the planet's close orbit around its star. Stellar tides would be much stronger than lunar tides on Earth, potentially creating dramatic tidal ranges that expose and flood vast coastal areas twice per 8.8-day orbital period. These extreme tides could create unique environments where life adapts to rapid changes between aquatic and terrestrial conditions. The discovery of LP 899c highlights how rapidly our knowledge of exoplanets is expanding. Just a few years ago, finding a potentially habitable planet was front-page news. Now, astronomers discover several potentially habitable worlds each year, and the challenge has shifted from finding these planets to studying them in detail to determine which ones actually harbor life. The planet's proximity to Earth makes it an ideal laboratory for testing new techniques for atmospheric analysis and characterization. Scientists plan to use LP 899c as a prototype for studying similar planets that might be discovered around even closer stars in the future. Recent computer simulations suggest that LP 899c could maintain liquid water across a wide range of atmospheric conditions, making it more likely to be habitable than planets that require very specific atmospheric compositions. This robustness to different environmental conditions increases the chances that this world could actually support life. The ongoing study of LP 899c represents the cutting edge of exoplanet science, where new discoveries happen so quickly that our understanding of potentially habitable worlds continues to evolve month by month. But while this newly discovered planet offers fresh possibilities, our next destination takes us to a calmer, more stable world that might represent the ideal environment for long-term biological evolution. 11 light-years from Earth, a planet slightly larger than our world orbits one of the calmest red dwarf stars ever discovered, creating what might be the most stable environment for life in our local cosmic neighborhood. Ross 128b receives energy levels similar to Earth, but its star produces virtually none of the dangerous flares and radiation storms that plague most red dwarf systems, making this world a potential oasis of tranquility in a galaxy where stellar violence often destroys planetary atmospheres. This remarkable planet completes one orbit around its star every 9.9 days, positioning it in the perfect zone where liquid water could exist on its surface. The star Ross 128 burns with exceptional stability, showing almost no variation in brightness or magnetic activity over the decades that astronomers have monitored it. This stellar calm means that Ross 128b has probably enjoyed billions of years of consistent, gentle energy input, ideal conditions for life to evolve and flourish. The planet's size and mass create surface gravity about 1.4 times stronger than Earth's, strong enough to hold on to a substantial atmosphere, but not so strong as to create crushing conditions. If Ross 128b has an Earth-like atmosphere, the surface pressure would be higher than what we experience, but still comfortable for life forms similar to those on Earth. Ross 128b's proximity to Earth makes it one of the most scientifically valuable exoplanets ever discovered. At just 11 light-years away, this world is close enough that radio signals from Earth would take only 11 years to reach it, and any response would take another 11 years to return. If intelligent life exists on Ross 128b, we could potentially establish communication within a human lifetime. The stable stellar environment around Ross 128 creates opportunities for atmospheric complexity that don't exist around more active stars. Without constant bombardment by stellar flares, Ross 128b could have developed and maintained a layered atmosphere with distinct regions for different chemical processes. An ozone layer could protect surface life from ultraviolet radiation, while water clouds could regulate temperature through reflection and greenhouse effects. Computer models suggest that Ross 128b might experience weather patterns remarkably similar to Earth's, despite its rapid 9.9-day orbit. If the planet is tidally locked, the boundary between the day and night sides could host a permanent storm system that redistributes heat around the planet, creating moderate temperatures across the entire surface. The planet's likely tidal locking creates interesting possibilities for how life might evolve there. The permanently lit day side could support photosynthetic organisms that never experience night, while the dark side might harbor chemosynthetic life forms that derive energy from chemical processes rather than sunlight. The twilight zone between these regions could host the most diverse ecosystems where both types of life could coexist. Recent observations using the European Southern Observatory's telescopes have revealed hints that Ross 128b might have a substantial atmosphere. Measurements of how the planet's infrared radiation changes as it orbits its star suggest the presence of atmospheric gases that trap and redistribute heat. These observations represent some of the most detailed atmospheric studies ever conducted on such a distant world. The calm nature of Ross 128 means that any magnetic field generated by the planet's core would provide excellent protection against the gentle stellar wind. Unlike planets around active stars that need strong magnetic fields to survive, Ross 128b could maintain a protective magnetic bubble even with a relatively weak planetary magnetic field. If Ross 128b has oceans, they would be among the most stable bodies of water in the galaxy. Without stellar flares to drive extreme weather or tidal forces to create massive waves, these oceans could maintain consistent temperatures and chemistry for billions of years. Such stability would allow marine ecosystems to develop incredible complexity and diversity. The planet's surface temperature likely remains remarkably constant due to the stable stellar output. Without the dramatic temperature swings that plague planets around variable stars, life on Ross 128b wouldn't need to evolve extreme temperature tolerance. This could allow for more delicate and specialized organisms that couldn't survive in harsher environments. Scientists have proposed Ross 128b as an ideal target for the next generation of extremely large telescopes currently under construction. These instruments might be powerful enough to directly photograph the planet's surface, revealing continents, oceans, and cloud patterns that could provide direct evidence of habitability or even biological activity. The discovery of Ross 128b has influenced how astronomers search for potentially habitable planets. Rather than focusing only on planets in habitable zones, scientists now prioritize worlds around calm, stable stars that could provide the long-term environmental stability necessary for complex life to evolve. But while Ross 128b represents stability and calm, our next destination takes us to a planet much closer to home, orbiting a star that we can see with the naked eye from Earth's surface, just 11.9 light-years from Earth. A super-Earth 4 times more massive than our world orbits a star so similar to our Sun that astronomers have studied it for decades as a solar analog. Tau Ceti A completes one orbit every 168 days, positioning it near the inner edge of its star's habitable zone, where liquid water could potentially exist on its surface, making this world one of the closest potentially habitable planets to Earth. Tau Ceti, the star at the center of this system, has captured human imagination for generations because it's visible to the naked eye from Earth and burns with characteristics remarkably similar to our Sun. The star contains slightly less metal than our Sun, which affects planetary formation in ways that could make Tau Ceti E a very different world from Earth, despite its favorable position in the habitable zone. The planet's substantial mass creates surface gravity about twice as strong as Earth's, which would profoundly affect how any atmosphere and hydrosphere behave. The stronger gravity allows Tau Ceti to hold onto a much thicker atmosphere than Earth possesses, potentially creating surface pressures several times higher than what we experience. This thick atmosphere could trap enough heat to keep the planet warm despite receiving only about 60% of the energy that Earth gets from our Sun. Here's where the story gets complicated. Computer models suggest that Tau Ceti E might be experiencing a runaway greenhouse effect, similar to what happened on Venus. The planet's position near the inner edge of the habitable zone, combined with its ability to hold onto a thick atmosphere, could have led to surface temperatures hot enough to boil water. Instead of a habitable world, Tau Ceti E might be a cautionary tale, about how quickly planetary atmospheres can spiral out of control. However, other models propose a more optimistic scenario. If Tau Ceti has highly reflective clouds or surface features, it might be able to bounce enough stellar energy back into space to maintain moderate temperatures despite its challenging orbital position. The planet could exist in a delicate balance where small changes in cloud cover or atmospheric composition determine whether it remains habitable or becomes a steam-covered hell world. The Tau Ceti system presents unique challenges for planetary habitability due to its debris disk, a ring of asteroids and comets that creates a much more dangerous environment than our solar system. Tau Ceti probably experiences asteroid and comet impacts at rates 10 times higher than Earth, creating a constantly changing surface where crater formation and volcanic activity reshape the landscape on relatively short timescales. These frequent impacts could actually help maintain habitability by providing a mechanism for recycling atmospheric gases and delivering water and organic compounds to the planet's surface. Each major impact would vaporize part of the surface, releasing trapped gases and potentially providing the energy needed to drive complex atmospheric chemistry. The planet's 168-day orbit creates seasons that last about 42 Earth days each, much shorter than Earth's seasons, but long enough to drive significant climate variations. If Tau Ceti has an atmosphere capable of storing and releasing heat, these rapid seasonal changes could create dynamic weather patterns that distribute energy around the planet. Recent observations using advanced ground-based telescopes have attempted to detect atmospheric signatures from Tau Ceti, but the results remain inconclusive. The planet's proximity to its bright star makes it extremely difficult to isolate the faint signal of reflected light that would reveal atmospheric composition. Future space telescopes with better capabilities for blocking stellar light might finally determine whether this world has the thick atmosphere that models predict. The possibility of life on Tau Ceti depends heavily on how well organisms could adapt to the high-impact environment and potentially extreme atmospheric conditions. Life forms might need to evolve sophisticated repair mechanisms to deal with radiation from frequent impacts, or they might retreat to underground environments where they're protected from surface catastrophes. If Tau Ceti has maintained liquid water despite its challenging conditions, those oceans would be unlike anything on Earth. The high atmospheric pressure could allow water to remain liquid at temperatures well above Earth's boiling point, creating hot, dense seas that could support exotic biochemistry based on thermophilic organisms. The planet's proximity to Earth makes it a prime target for future interstellar missions. At less than 12 light-years away, Tau Ceti could potentially be reached by advanced spacecraft within a century or two, making it one of the most likely destinations for humanity's first journey to another potentially habitable world. Recent advances in telescope technology have allowed astronomers to study the Tau Ceti system in unprecedented detail, revealing that it might contain additional planets that could provide alternative habitable environments if Tau Ceti proves too extreme for life. But while Tau Ceti challenges us with questions about habitability in high-energy environments, our next destination takes us to a completely different type of world, a planet where water might be so abundant that land becomes a rare and precious commodity. 1,200 light-years away, a planet 1.4 times Earth-size orbits at the outer edge of its star's habitable zone, and computer models suggest something extraordinary. This world might be completely covered by a global ocean with no continents or islands breaking the surface. Kepler-62 represents our best candidate for a true water world, a planet where life would evolve entirely in aquatic environments and where the concepts of land and sky might be completely alien. This super-Earth completes one orbit around its star every 267 days, positioning it at roughly the same distance from its sun as Venus sits from ours. However, Kepler-62's star burns much cooler and dimmer than our sun, providing just the right amount of energy to keep Kepler-62's global ocean from freezing solid while preventing it from boiling away into space. The planet's larger size creates several conditions that favor the development of a water world. The stronger gravity helps Kepler-62 hold onto a thick atmosphere that could trap enough heat to keep water liquid even at its distant orbit. Additionally, the planet's formation process likely delivered much more water than Earth received, creating oceans that could be hundreds of miles deep enough to cover any mountains or continents that might try to rise above the surface. Here's what makes Kepler-62 particularly intriguing. Without continents to create shallow seas and tidal zones, life would need to evolve in a completely three-dimensional environment. There would be no beaches, no coral reefs in shallow water, and no transition zones between aquatic and terrestrial life. Instead, ecosystems would develop in layers throughout the water column, from the sunlit surface zones down to the crushing depths near the ocean floor. The global ocean would create weather patterns unlike anything on Earth. Without land masses to disrupt airflow, Kepler-62 could develop planet-spanning storm systems that circle the globe in massive spirals. These super hurricanes might persist for months or years, driven by the temperature differences between the warm equatorial waters and the cooler polar regions. Marine life on Kepler-62 would face unique evolutionary pressures. Without shallow water environments, organisms might need to evolve sophisticated buoyancy control to navigate the vast three-dimensional ocean. Swimming creatures could potentially grow much larger than anything in Earth's oceans, taking advantage of the deep water and lack of size constraints imposed by shallow areas. The absence of land would create challenges for developing technology and civilization. Any intelligent life that evolved on Kepler-62 would need to build tools and structures from materials available in the ocean, perhaps growing coral-like cities or developing biotechnology based on modified marine organisms. The concept of fire, metallurgy, and many other land-based technologies would be completely foreign to ocean-dwelling intelligence. Computer models suggest that Kepler-62's thick atmosphere might create a substantial greenhouse effect that keeps the entire planet at moderate temperatures, potentially allowing liquid water to exist even at the polar regions. The global ocean would act as a massive heat reservoir, storing thermal energy during the planet's day and releasing it during the night to maintain stable temperatures. The planet's 267-day orbit creates long seasons that would drive major changes in ocean circulation patterns. As different hemispheres receive more or less stellar energy during the planet's year, massive currents would develop to redistribute heat around the globe, creating seasonal migrations of nutrients and marine life that could span thousands of miles. Deep beneath Kepler-62's global ocean, the seafloor might host extensive hydrothermal vent systems where volcanic activity provides energy for chemosynthetic ecosystems. These deep-sea communities could develop independently of surface life, creating parallel evolutionary pathways that lead to completely different types of organisms. The thick atmosphere and global ocean would create unique optical effects that would make Kepler-62's sky unlike anything we see on Earth. Light filtering through the dense air and reflecting off the ocean's surface could create perpetual rainbows, while the lack of land features would mean that the horizon appears perfectly smooth in all directions. Recent atmospheric modeling suggests that Kepler-62 might have clouds that form at multiple altitudes, creating layered weather systems that could produce complex precipitation patterns. Rain, snow, and possibly even more exotic forms of precipitation could fall through the thick atmosphere into the global ocean, driving chemical cycles that support marine ecosystems. If life exists on Kepler-62, it would represent a completely independent experiment in biological evolution, developing in an environment so different from Earth that the resulting organisms might challenge our basic assumptions about how life can adapt and thrive. The study of Kepler-62 helps scientists understand how common water worlds might be throughout the galaxy, and whether such planets could support complex life despite their lack of traditional land-based environments. But while Kepler-62 shows us the possibilities of life in a global ocean, our next destination takes us beyond individual planets to explore how new techniques for studying distant atmospheres are revolutionizing our understanding of habitability across the galaxy. 1,150 light-years from Earth, a planet slightly smaller than Jupiter has become one of the most thoroughly studied worlds in our galaxy, not because it could harbor life, but because it's teaching us how to detect the atmospheric signatures that could reveal habitability on distant Earth-like planets. WASP-96b orbits so close to its star that its atmosphere reaches 2000 degrees Fahrenheit, creating a natural laboratory where astronomers can perfect the techniques that will eventually find signs of life on more hospitable worlds. This hot gas giant completes one orbit around its star every 3.4 days, making it what astronomers call a hot Jupiter, a massive planet that migrated inward from the outer regions of its solar system to orbit dangerously close to its star. The extreme heat has puffed up WASP-96b's atmosphere, making it larger and less dense than Jupiter despite having similar mass. The planet's inflated atmosphere creates ideal conditions for atmospheric spectroscopy, the technique that allows scientists to identify gases in distant planetary atmospheres by analyzing how they absorb starlight. When WASP-96b passes in front of its star, different atmospheric gases absorb specific wavelengths of light, creating a chemical fingerprint that reveals the atmosphere's composition in remarkable detail. Recent observations using the James Webb Space Telescope have detected water vapor, clouds, and haze in WASP-96b's atmosphere with unprecedented precision. While this scalding world could never support life, the same techniques used to study its atmosphere can be applied to potentially habitable planets to search for water, vapor, oxygen, ozone, and other gases that could indicate biological activity. The breakthrough came from analyzing how starlight changes color as it filters through WASP-96b's atmosphere during transit. Different molecules absorb different wavelengths of light. So by measuring which colors of light get absorbed, scientists can determine exactly which gases exist in the planet's air. This technique works so well that astronomers can detect atmospheric components that make up less than 1 part per million of the total atmosphere. WASP-96b's atmosphere contains water vapor. Despite surface temperatures hot enough to melt copper, this discovery proves that water can survive in planetary atmospheres under much more extreme conditions than scientists previously thought, expanding the range of planets where we might expect to find water signatures in the future. The planet's cloud formations have revealed unexpected complexity in hot Jupiter atmospheres. High-altitude clouds made of condensed metals and exotic compounds create weather patterns that span thousands of miles, driven by temperature differences between the day and night sides of the tidally locked planet. These massive storm systems redistribute heat and chemicals around the planet in ways that create detectable variations in the atmospheric spectrum. Scientists use WASP-96b as a benchmark for testing new atmospheric analysis techniques before applying them to potentially habitable planets. The planet's bright star and clear atmospheric signatures make it easier to study than smaller, cooler worlds, allowing researchers to refine their methods and understand the limitations of their instruments. The atmospheric analysis has revealed that WASP-96b contains significantly less sodium than similar planets, suggesting that this world formed in a different region of its solar system or experienced different evolutionary processes. These compositional differences teach scientists how planetary formation affects atmospheric chemistry, providing insights that help interpret observations of potentially habitable worlds. Temperature mapping of WASP-96b's atmosphere has shown that the day side reaches over 2000 degrees Fahrenheit, while the night side stays slightly cooler, creating powerful winds that transport heat around the planet. Understanding these heat transport mechanisms helps scientists model atmospheric circulation on planets in habitable zones, where similar processes could determine whether a world maintains moderate temperatures suitable for life. The planet study has pioneered techniques for detecting atmospheric escape, where hot gases stream away from the planet into space. WASP-96b loses thousands of tons of atmosphere every second, but its massive size means it can sustain this loss for billions of years. Similar measurements on smaller planets could reveal whether they've retained enough atmosphere to support habitability. Recent observations have detected subtle chemical reactions happening in WASP-96b's upper atmosphere, where ultraviolet radiation from the star breaks apart molecules and creates new compounds. These atmospheric chemistry studies provide templates for understanding how stellar radiation affects planetary atmospheres, crucial information for assessing habitability around different types of stars. The precision achieved in studying WASP-96b's atmosphere represents a revolution in exoplanet science. For the first time, scientists can analyze the detailed chemical composition of a world orbiting another star, bringing us tantalizingly close to the day when we might detect definitive biosignature gases in the atmosphere of a potentially habitable planet. The techniques developed through studying WASP-96b are now being applied to smaller, cooler planets that might actually harbor life. Each atmospheric analysis brings us one step closer to answering the fundamental question of whether Earth is unique or whether life exists throughout the galaxy. But while WASP-96b shows us how to detect atmospheric signatures, our next destination takes us to a world that has already generated mysterious signals that briefly made scientists wonder if we had detected our first sign of alien intelligence. 94 light-years from Earth, a planet slightly larger than Neptune orbits a sun-like star. And in 2016, this distant world became the center of one of the most intriguing potential SETI detections in recent history, when radio telescopes picked up a strong signal that seemed to originate from the HD 164,595 system. While the signal was later explained as terrestrial interference, the incident highlighted how close we might be to detecting genuine communications from distant civilizations. HD 164,595b completes one orbit around its star every 40 days, positioning it too close to its sun to be habitable by Earth standards. Surface temperatures likely exceed 1,000 degrees Fahrenheit, making this world inhospitable to life as we know it. However, the planet's discovery raised intriguing questions about whether other, more habitable worlds might exist in the same system, potentially harboring the intelligent life that could have produced the mysterious radio signal. The signal detected from HD 164,595 registered at a frequency of 11 GHz, with a strength that would have required enormous amounts of energy to produce if it truly originated from the star system. The power levels were so high that any civilization capable of generating such a signal would need technology far beyond anything humans have developed, potentially representing a Type 2 civilization on the Kardashev scale, one capable of harnessing the entire energy output of its star. Radio astronomers initially struggled to explain the signal's characteristics. It lasted for several minutes, showed no obvious pattern or modulation that would indicate natural origin, and came from a precise direction in space that corresponded to the HD 164,595 system. The signal's frequency and duration matched theoretical predictions for how an advanced alien civilization might attempt to communicate with distant worlds. Follow-up observations using multiple radio telescopes around the world failed to detect any repeat signals from HD 164,595, which raised immediate skepticism about the extraterrestrial origin theory. Genuine signals from alien civilizations would likely repeat or show some pattern of transmission, rather than appearing once and never returning. The lack of follow-up signals suggested that the original detection might have been caused by human technology rather than alien intelligence. The investigation into the HD 164,595 signal revealed how difficult it can be to distinguish between genuine extraterrestrial communications and terrestrial interference. Satellites, military radar systems, and even microwave ovens can produce radio signals that appear to come from space when they reflect off aircraft or satellites in Earth's orbit. The HD 164,595 signal was eventually traced to a military satellite that briefly transmitted on the same frequency as the apparent alien signal. However, the incident provided valuable lessons for the search for extraterrestrial intelligence, SETI community. It demonstrated how quickly potentially significant signals can be detected and analyzed, and it showed that the international astronomy community is prepared to investigate unusual signals with appropriate scientific rigor. The protocols developed for investigating the HD 164,595 signal now serve as templates for evaluating future potential SETI detections. The HD 164,595 system itself remains scientifically interesting, even without alien signals. The star is remarkably similar to our Sun in mass, temperature, and age, making it the type of star most likely to support habitable planets. While HD 164,595b is too hot for life, computer models suggest that additional planets could exist in the system's habitable zone, potentially providing environments where liquid water and life could exist. Advanced telescopic searches have not yet detected any additional planets in the HD 164,595 system, but current instruments can only find relatively large planets that pass directly in front of their star, as seen from Earth. Earth-sized planets in the habitable zone could easily exist in this system without being detectable by current technology, leaving open the possibility that HD 164,595 hosts worlds where life might actually evolve. The false alarm at HD 164,595 highlights both the promise and the challenges of searching for extraterrestrial intelligence. Radio telescopes are now sensitive enough to detect artificial signals from civilizations thousands of light years away, but they're also sensitive enough to detect countless sources of interference from human technology. Distinguishing between genuine alien signals and false alarms requires careful analysis and multiple independent confirmations. Recent improvements in radio telescope technology and signal processing have reduced the likelihood of false SETI detections while increasing sensitivity to genuine extraterrestrial signals. Automated systems now monitor millions of stars simultaneously, looking for the types of artificial signals that could only be produced by intelligent civilizations. The HD 164,595 incident reminds us that the discovery of extraterrestrial intelligence might come not from a carefully planned observation of a nearby, potentially habitable planet, but from an unexpected signal detected during routine monitoring of star systems that seemed unremarkable. Any star system could potentially harbor intelligent life, even if the planets we've detected there seem unsuitable for biology. The continued study of HD 164,595 and similar systems keeps alive the possibility that somewhere among the thousands of known exoplanets, a civilization might be trying to communicate with us right now, sending signals across the vast distances of interstellar space in hopes of making contact with other intelligent species. But while HD 164,595b teased us with the possibility of alien intelligence, our next destination takes us to a world that sits precariously on the edge between habitability and hostile conditions, where the difference between life and death might come down to the thickness of the atmosphere. 16 light-years from Earth, a super-Earth 5 times more massive than our world orbits at the very edge of its star's habitable zone, where computer models suggest it could be either a temperate planet with flowing water or a runaway greenhouse world with surface temperatures hot enough to melt lead. Gliese 832c represents one of the most uncertain cases in our catalog of potentially habitable planets, a world where small differences in atmospheric composition could determine whether it supports life or remains forever barren. This massive planet completes one orbit around its red dwarf star every 36 days, positioning it at the inner boundary of the zone where liquid water could theoretically exist on its surface. The planet receives about the same amount of energy from its star as Earth receives from our Sun, but its larger mass allows it to hold onto a much thicker atmosphere that could either provide beneficial greenhouse warming or trigger catastrophic overheating. The uncertainty surrounding Gliese 832c stems from our limited understanding of how super-Earth atmospheres behave. Computer models produce dramatically different results depending on the assumptions about atmospheric composition, with some scenarios showing moderate Earth-like temperatures and others predicting Venus-like conditions with surface temperatures exceeding 800 degrees Fahrenheit. In the optimistic scenario, Gliese 832c has developed an atmosphere with just the right amount of greenhouse gases to maintain moderate temperatures despite its position at the edge of the habitable zone. Water vapor, carbon dioxide, and other gases could create a blanket effect that keeps the planet warm enough for liquid water while reflecting enough heat back into space to prevent runaway warming. However, the pessimistic scenario paints a much darker picture. The planet's strong gravity could have allowed it to retain hydrogen and helium from its formation, creating a thick primordial atmosphere that traps enormous amounts of heat. Alternatively, volcanic outgassing over billions of years could have pumped so much carbon dioxide into the air that Gliese 832c now experiences a runaway greenhouse effect, similar to Venus. The planet's 36-day orbit creates seasonal variations that could play a crucial role in determining its climate stability. As Gliese 832c moves closer and farther from its star during its slightly elliptical orbit, the changing energy input could either stabilize temperatures through feedback mechanisms or push the planet back and forth between different climate states. Recent attempts to detect atmospheric signatures from Gliese 832c have produced inconclusive results. The planet's red dwarf star is much dimmer than Sun-like stars, making it difficult to gather enough light to analyze the planet's atmospheric composition using current telescope technology. Future instruments with greater sensitivity might finally determine whether this world has maintained a habitable atmosphere or succumbed to greenhouse warming. The star Gliese 832 presents both advantages and challenges for planetary habitability. Red dwarf stars burn for trillions of years, providing stable energy for much longer than Sun-like stars. However, many red dwarfs produce violent flares during their youth that can strip away planetary atmospheres. Gliese 832 appears to be relatively calm, but any historical flare activity could have dramatically altered the planet's atmospheric evolution. If Gliese 832c has maintained habitable conditions, it would experience a very different environment from Earth due to its strong gravity and rapid orbit. Surface gravity 5 times stronger than Earth's would make movement challenging for any life forms, but it would also allow for much thicker atmospheres and more dramatic weather patterns than we see on our planet. The planet's likely tidal locking creates additional complexity in climate modeling. With one hemisphere permanently facing the star and the other in eternal darkness, temperature differences between the day and night sides could drive powerful atmospheric circulation patterns that either stabilize global temperatures or create extreme weather conditions incompatible with life. Atmospheric escape represents another critical factor in Gliese 832c's habitability. Even though the planet's strong gravity helps it retain atmospheric gases, the close orbit exposes it to intense stellar radiation that could gradually strip away lighter atmospheric components over billions of years. The balance between atmospheric retention and loss could determine whether this world remains habitable over geological timescales. Scientists use Gliese 832c as a test case for developing better climate models for super-Earth planets. The uncertainties surrounding this world highlight the gaps in our understanding of how planetary atmospheres evolve around red dwarf stars, driving research that will help us better assess the habitability of similar planets discovered in the future. The ongoing debate about Gliese 832c's habitability illustrates how much we still need to learn about exoplanet atmospheres. Even with our most sophisticated computer models and observational techniques, we cannot definitively determine whether this nearby world represents a potential home for life or a cautionary tale about the fragility of planetary climates. Future missions to study Gliese 832c could provide crucial insights into super-Earth habitability that would inform our understanding of potentially habitable planets throughout the galaxy. The lessons learned from this uncertain world could help us identify which of the thousands of known exoplanets are most likely to actually support life. But while Gliese 832c challenges us with questions about atmospheric stability, our next destination takes us to an even more dangerous world, a planet that might have all the right conditions for life, except for the deadly radiation that regularly bathes its surface. 470 light-years away, a planet just 12% larger than Earth orbits squarely in its star's habitable zone, receiving almost exactly the same amount of energy that Earth gets from our Sun. Kepler 438b should be one of the most promising candidates for habitability in our galaxy. Yet, this world faces a deadly challenge that could make its surface uninhabitable for any known form of life. It orbits a red dwarf star that regularly unleashes radiation flares 10 times more powerful than the most violent solar props. Storms our sun has ever produced. This near-Earth-sized world completes one orbit around its star every 35 days, positioning it at the perfect distance where liquid water could exist on its surface under normal circumstances. The planet's size suggests it likely has similar gravity to Earth, and computer models indicate it could maintain an Earth-like atmosphere, if not for the constant bombardment of high-energy radiation from its hyperactive star. Kepler 438, the red dwarf star at the center of this system, represents one of the most magnetically violent stars known to astronomy. Every few hundred days, the star produces superflares that increase its brightness by up to 10% and blast nearby planets with X-rays and ultraviolet radiation intense enough to strip away atmospheric gases molecule by molecule. These radiation storms make the most powerful solar flares from our sun look like gentle breezes by comparison. The regular superflares create a hostile environment that would challenge even the most radiation-resistant life forms known on Earth. During a typical flare event, Kepler 438b receives about 100 times more high-energy radiation than Earth experiences during the most intense geomagnetic storms. This level of radiation would break apart water molecules in the atmosphere, destroy ozone layers, and create surface conditions lethal to most biological processes. However, the story of Kepler 438b might not be entirely hopeless. Computer simulations suggest that if the planet has a very strong magnetic field, housed much stronger than Earth's, it might be able to deflect enough of the stellar radiation to create small safe zones on its surface. These protected regions could potentially harbor life in underground caves or deep ocean environments where the worst radiation effects can't penetrate. The planet's atmosphere, if it still exists, would be in a constant state of flux due to the regular radiation bombardment. During calm periods between flares, atmospheric gases could accumulate and create more moderate surface conditions. But each superflare would strip away part of the atmosphere, creating a cycle where the planet's habitability waxes and wanes over periods of hundreds of Earth days. Recent atmospheric modeling suggests that Kepler 438b might have evolved unique atmospheric chemistry in response to the radiation environment. Gases that would normally be destroyed by ultraviolet light might persist due to rapid chemical recycling processes driven by the high-energy radiation. The result could be an atmosphere unlike anything in our solar system, with exotic chemistry that could either support unusual forms of life or make the surface completely inhospitable. The planet's 35-day orbit creates another layer of complexity in its radiation environment. As Kepler 438b moves closer and farther from its star during its slightly elliptical orbit, the intensity of radiation bombardment varies significantly. The planet might experience periods of relative calm alternating with times of intense radiation exposure, creating environmental cycles that could drive unique evolutionary adaptations. If life exists on Kepler 438b, it would need to be extraordinarily resilient to radiation damage. Organisms might evolve sophisticated DNA repair mechanisms that can fix genetic damage caused by high-energy particles, or they might develop cellular structures that shield vital components from radiation exposure. Some life forms might even evolve to use the abundant high-energy radiation as a source of energy rather than relying on chemical processes or photosynthesis. The underground environment on Kepler 438b could provide refuge from surface radiation while still allowing for complex ecosystems. Caves, underground rivers, and subsurface oceans could host communities of organisms that emerge to the surface only during the calm periods between stellar flares. These underground biospheres could persist for billions of years, completely isolated from the hostile surface conditions. The study of Kepler 438b has influenced how scientists think about habitability around red dwarf stars. While these small stars provide stable energy for trillions of years, their tendency to produce violent flares might make them less suitable for supporting life than previously thought. This research has led to renewed interest in planets around Sun-like stars, which provide more consistent and less dangerous radiation environments. Recent advances in telescope technology might soon allow direct detection of atmospheric escape from Kepler 438b, providing definitive evidence of how stellar flares affect planetary atmospheres. These observations could determine whether this potentially habitable world has managed to retain enough atmosphere to support life despite the constant radiation bombardment. The ongoing study of Kepler 438b represents a crucial test of life's ability to survive in high radiation environments. If biological processes can persist on this battered world, it would dramatically expand our understanding of where life might exist throughout the galaxy, including around the most common type of stars in the Milky Way. But while Kepler 438b shows us the challenges of surviving stellar violence, our journey now approaches its climax, as we explore what the future might hold for our search for life among the stars. Somewhere in our galaxy, orbiting a star we haven't yet identified, a planet waits that will transform humanity's understanding of our place in the universe. This world might be closer than Proxima Centauri b, or farther than Kepler 452b, larger than a super-Earth or smaller than Mars. But when we find it, this planet will provide the first unambiguous evidence that life exists beyond Earth, ending the cosmic loneliness that has defined human existence for our entire history. The discovery might come from the James Webb Space Telescope detecting oxygen and water vapor in the atmosphere of a planet orbiting a nearby red dwarf star. Oxygen is so reactive that it disappears from planetary atmospheres within a few million years, unless something continuously replenishes it, and on Earth, that something is life. Finding oxygen in another world's atmosphere, especially combined with water vapor and other biological gases, would represent the smoking gun evidence that biology has taken hold on another world. Alternatively, the breakthrough might come from radio telescopes detecting artificial signals from a civilization thousands of light years away. These signals could be anything from deliberate attempts at interstellar communication to the accidental leakage of powerful transmissions from an advanced technological society. The first confirmed detection of extraterrestrial intelligence would reveal that not only does life exist elsewhere, but that evolution can produce consciousness and technology on multiple worlds. The discovery could even come from much closer to home, within our own solar system. Upcoming missions to Jupiter's moon Europa and Saturn's moon Enceladus will search for life in the subsurface oceans that exist beneath these worlds' icy crusts. Finding even microbial life in these alien seas would prove that biology can arise independently in multiple locations within a single star system, suggesting that life might be extraordinarily common throughout the galaxy. Advanced artificial intelligence might accelerate the pace of discovery by analyzing vast datasets from space telescopes in ways that human scientists never could. Machine learning algorithms could identify subtle patterns in exoplanet observations that reveal atmospheric biosignatures currently hidden in the noise of stellar variation. AI systems might discover hundreds of potentially habitable worlds in existing data that we've overlooked using traditional analysis methods. The next generation of extremely large telescopes currently under construction will revolutionize our ability to study exoplanet atmospheres. These instruments will be powerful enough to directly photograph Earth-sized planets orbiting nearby stars, revealing not just atmospheric composition but also surface features like continents, oceans, and cloud patterns. We might see weather systems on alien worlds, watch seasonal changes unfold on distant planets, and observe the day-night boundaries on tidally locked worlds. Future space missions could take atmospheric analysis to unprecedented levels of precision. Proposed space telescopes designed specifically for exoplanet observation could detect biosignature gases at concentrations millions of times lower than current instruments can achieve. These missions could not only confirm the presence of life, but also determine what types of organisms exist on distant worlds by analyzing the specific chemical fingerprints they leave in planetary atmospheres. The discovery of life beyond Earth will likely come not from a single dramatic observation, but from the gradual accumulation of evidence across multiple worlds and multiple types of observations. We might first detect possible biosignatures in the atmosphere of one planet, then find similar signatures on several other worlds, building a case for extraterrestrial life through statistical analysis rather than definitive proof from any single planet. Advances in theoretical biology might help us recognize forms of life that don't match terrestrial biology. Scientists are developing models for how life might evolve using different chemical foundations than Earth biology, potentially based on silicon instead of carbon or using liquid methane instead of water. Recognizing these alternative forms of life could expand our search to include worlds that currently seem too hostile for biology. The implications of discovering extraterrestrial life will extend far beyond science into philosophy, religion, and human culture. Finding even microbial life on another world would prove that Earth is not unique, while discovering intelligent extraterrestrial civilizations would fundamentally change how humans see themselves in the cosmic order. These discoveries could unite humanity around our shared identity as one species among many in a galaxy teeming with life. International cooperation in space exploration will become even more crucial as we move closer to detecting extraterrestrial life. The discovery will likely require confirmation from multiple independent sources and careful analysis by scientists from around the world. The protocols we develop for announcing and studying the first confirmed extraterrestrial life will set precedents for how humanity handles one of the most significant discoveries in our history. The search for life beyond Earth represents more than just scientific curiosity. It addresses fundamental questions about whether intelligence and consciousness are rare cosmic accidents or inevitable outcomes of planetary seventh evolution. The answers we find among the stars will determine whether humanity faces the future alone or as part of a vast community of conscious beings scattered throughout the galaxy. But as we stand on the threshold of these magnificent discoveries, we must also consider what all these distant worlds mean for humanity's own cosmic journey. The catalog of potentially habitable exoplanets we've explored represents more than a list of distant curiosities. These worlds chart a roadmap for humanity's expansion beyond Earth and offer glimpses of what our species might become as we spread among the stars. From the tidally locked Proxima Centauri b, just 4 light-years away, to the ancient Kepler 452b, showing us Earth's far future, each of these planets teaches us something crucial about the challenges and opportunities that await us in the cosmos. Our nearest potentially habitable neighbor, Proxima Centauri b, could become humanity's first destination beyond our solar system. At 4.2 light-years away, this world represents the closest we can come to interstellar travel with technologies we might develop within the next century. Advanced spacecraft using fusion propulsion, or even more exotic technologies like antimatter engines, could potentially reach Proxima Centauri b within 50 to 100 years, making it possible for humans alive today to see our species take its first steps toward becoming an interstellar civilization. The diverse range of habitable worlds we've discovered expands our options for future colonization far beyond Earth-like planets. Super-Earths like LHS 1000, 140b, and TOI 715b show us that habitable worlds might typically be larger and more massive than Earth, with stronger gravity and thicker atmospheres. Humans settling such worlds would need to adapt to these conditions, perhaps developing new technologies for movement and construction in high-gravity environments, or even evolving different physical characteristics over many generations. Tidally locked planets like TRAPPIST-1e and Gliese 167cc challenge us to think creatively about how human civilization might develop on worlds where one side experiences eternal day while the other remains in permanent night. These planets could host cities in the twilight zones where temperatures remain moderate, with transportation networks connecting the resource-rich day sides to the energy-generating facilities that could harness the temperature differences between hemispheres. The water worlds like Kepler 62 hint at completely different types of human societies that might develop on planets with no land masses. Floating cities, underwater habitats, and marine-based agriculture could support human populations on worlds covered entirely by deep oceans. These aquatic civilizations might develop technologies and cultures radically different from anything possible on land-based worlds. The violent stellar environments around planets like Wolf 1000 and 61Ek and Kepler 438b could drive the development of advanced radiation, shielding technologies, and underground civilizations. Humans settling such worlds might become masters of defensive technology, building cities deep beneath planetary surfaces and developing biotechnology that enhances radiation resistance. These skills could prove invaluable for surviving in other hostile environments throughout the galaxy. The long-term survival of human civilization might depend on spreading across multiple star systems to avoid catastrophic events that could affect entire solar systems. Supernova explosions, gamma-ray bursts, and other cosmic disasters could sterilize planets across hundreds of light years, but a civilization distributed among many star systems would be virtually impossible to destroy completely. The exoplanets we've discovered provide thousands of potential refuges for humanity's future. Each potentially habitable world offers unique opportunities for scientific research and technological development. The extreme conditions on planets like TOI 849b could advance materials science and high-energy physics, while the atmospheric complexity of worlds like K2-18b could drive innovations in climate engineering and atmospheric management. Human settlements across diverse exoplanets could become specialized research centers that push the boundaries of knowledge in different fields. The discovery of extraterrestrial life on any of these worlds would fundamentally change humanity's cosmic perspective and priorities. Finding even microbial life would prove that biology can arise independently on multiple worlds, suggesting that life is common throughout the galaxy. Discovering intelligent alien civilizations would create opportunities for cultural and technological exchange that could accelerate human development by thousands of years. The challenges of reaching and settling exoplanets will drive technological innovations that benefit life on Earth as well. Developing closed-loop life support systems for interstellar journeys could help solve environmental problems on Earth, while learning to terraform hostile exoplanets could provide tools for reversing climate change or adapting to environmental shifts on our home world. As we contemplate humanity's expansion to the stars, we must also consider our responsibilities as a spacefaring species. The potentially habitable worlds we've discovered might already harbor life, requiring us to develop ethical frameworks for interacting with alien ecosystems and protecting extraterrestrial environments. Human settlements on exoplanets must balance the needs of human civilization with respect for any existing biological communities. The journey to these distant worlds will likely span many human generations, requiring us to develop sustainable space-based civilizations that can maintain themselves during century-long voyages between stars. These traveling communities could become their own unique cultures, potentially as different from Earth-based humanity as any alien civilization we might encounter. The potentially habitable exoplanets scattered throughout our local region of the galaxy represent stepping stones toward an even grander future, a time when human civilization spans hundreds or thousands of star systems, when our species has become truly cosmic in scope. Each world we've explored brings us closer to understanding what that future might look like and how we might achieve it. The stars are calling, and these distant worlds light the way forward. Humanity's cosmic future begins with the next generation of space telescopes, interstellar probes, and perhaps even the first human missions beyond our solar system. The potentially habitable planets we've discovered today could become the homes where our descendants will live, work, and dream among alien suns, carrying the light of human consciousness to worlds we can barely imagine. From the twilight zones of tidally locked worlds to the crushing gravity of super-Earths, from the underground oceans of frozen planets to the metal vapor atmospheres of stellar survivors, our journey through the galaxy's most promising habitable worlds reveals a cosmos far stranger and more wonderful than we ever imagined. These 25 destinations represent just the beginning of humanity's search for life beyond Earth, and perhaps our first glimpse of the worlds where our species will someday call home. The potentially habitable exoplanets scattered throughout our cosmic neighborhood offer both hope and challenge. They show us that Earth-like conditions might be common throughout the galaxy. but they also reveal the incredible diversity of environments where life might arise. From planets battered by stellar radiation to worlds locked in permanent twilight, each destination teaches us something new about the possibilities and limits of habitability in our universe. As we stand on the threshold of an era when space telescopes will analyze alien atmospheres for signs of life, when interstellar probes might visit nearby star systems, and when humanity takes its first steps toward becoming a truly spacefaring civilization, these distant worlds light the way forward into our cosmic future. The next time you look up at the night sky, remember that among those countless points of light, worlds await where alien sunsets paint strange landscapes in colors we've never seen, where storms rage for decades across global oceans, and where life might already be writing its own remarkable story in the language of chemistry and evolution. Don't forget to subscribe for more cosmic journeys, and let me know in the comments which of these incredible worlds you'd most want to visit. The universe is vast, mysterious, and more amazing than we ever